Hi guys, in this video I want to talk to you about power. I want to first motivate why it's an important concept. It's not stressed so much in the AP or Regents, but I think it's a very useful idea, probably one of the more useful ideas in physics in terms of how it applies to everyday life. So example, what has more energy by weight? A chocolate chip cookie or TNT, the stuff in dynamite? By weight, which one has more energy in it? I might have asked you this question before, but think about it. The intuitive answer is the dynamite, right? But no, it's actually the cookie. The key difference in why we use TNT as an explosive and not cookies is because of the time factor. Our body breaks down the energy in food and cookies over the course of hours. The energy release in TNT happens in just such a fraction of a second, maybe like a millionth of a second. When that heat energy is released, it essentially vaporizes the air. It creates kind of a just high pressure gas that moves outwards, and that sends things flying. So that's kind of the basic difference between those two things. It's the component of time, and that's what power is. It takes that change in time into account. So equation wise, it is the change in energy over your time. The default unit of energy we use in physics is joules, and in time it's seconds. So the unit is joules per second, and we give it another name, watt. You might have heard this before, and I'll talk about examples in just a second. So intuitively, it's not just your energy change, it's how long it takes to release that energy. Okay, so some examples. This top equation is what you would see on the AP reference table. This bottom equation is what you would see in the Regents reference table. They mean the same thing, change in energy over time. On the Regents reference table, they're treating work as their change in energy, and work can be written as force times distance, and distance over time can be written as velocity. So these are how you can do numerical problems. I'll forward you to another video from A+ Physics. It does a good job of running through some numerical examples, I think. For now, I want to just focus on the concept. So some examples. Simple example. An apple is about 100 grams or 0.1 kilograms. And this is about a meter. This is about a meter. So if I lift a 1 kilogram apple up in 1 second, that is the change in energy you can see that I calculated for you. It's gravitational energy, mass times gravitational field strength, about 10 times 1 meter. And if I do this in about 1 second, that is roughly 1 watt. If I lift 2 apples, half a meter, that would be also 1 watt. So I want to bring it back to this video. I believe I shared I might have linked you to this before, but the Energy Slaves video. They were estimating each rower as outputting 250 watts. So think 250 apples being lifted 1 meter each second. That's kind of the output of those rowers using those machines. Another example, I measured it. My laptop, it's roughly 50 watts, ranging from 40 to 50 something, depending on the processing, like what I'm doing on the laptop. And a microwave, I looked it up. My microwave is about 1,000 watts. You can search up the owner's manual maybe, or it might be in the specs. Okay, so those are some examples of power. Let's look at application. What uses more energy per day? My laptop at 50 watts or microwave at 1,000 watts? Pause the video, think about it. It's kind of a trick question because you can't tell just based on the power rating. The power rating is like the rate of energy usage. But if you don't know how long it's being used for, then you can't answer that. So, going back to this, maybe I use my microwave 24 hours a day and I don't use my laptop at all. I guess think of it like a wage. If you are being paid, let's say, I don't know, $10 or $15 per hour, you don't know how much money you'll have over a certain amount of time unless you know the hours worked. So power is like that rate of time, rate of energy usage. That rate of energy usage. So you need to know the other time component to figure out the total, change in energy. So I worked out the math for you. I use my microwave roughly for 5 minutes. I don't use it too much, but 5 minutes a day. So at 1,000 watts, again, watts is joules per second. So I need to convert this minutes to seconds. So 60 seconds in a minute, the minutes cancels out. So 1,000 times 5 times 60 gets me about 300,000 joules. And my laptop gets me, if I use it for roughly 12 hours a day, or if it's on and basically being charged for at least 12 hours a day, then it's using about 2 million joules. So you can see that this number is getting pretty big. A joule is a really small amount. And if you look at your electric bill, you should look at your electric bill. You'll see that you're billed not in units of joules, but in units of kilowatt hours. So I didn't write this out on my slide, but to figure out the kilowatt hours, you'd basically need to know this 1,000 watts. It's probably easiest to convert it to kilowatts. So 1,000 watts is 1 kilowatt. And then you multiply it by the hours. So 5 minutes is 1/12 of an hour. So multiplied by the hours of usage. So that's like 1,000 divided by 12. And this is, well, that's 1 divided by 12 rather. 0.0, I'm just going to say 0.08 kilowatt hours. So that's how you would go from watts to kilowatts to hours. And again, this is over 1 day. Let's say I use my microwave for 5 minutes a day for 30 days. Then I would take this 0.08 kilowatt hours in 1 day, multiply it by 30, and I would get about 2.5. So that'd be the kilowatt hours per month, roughly, that my microwave would be contributing to my total energy usage. Okay. Next slide. Oh, I want to now just share with you a video. Talking through light bulbs. Okay, so here's the video. This is a Yankee scented candle. You can see that it is, this is moving a little too fast. Yankee scented candle. Wikipedia says it's about 80 watts, and the temperature is about 140, 150 plus degrees Celsius. So this right here is an incandescent bulb rated at 75 watts. They're pretty inefficient. You can see that it's about 83 watts up there, and registering maybe like 60 degrees Celsius, a little bit more, maybe even 70 to 80. So this is a 75 watt bulb. This right here is a 40 watt bulb. And you can see maybe a little bit quick, but the energy usage was about a little bit more than 40 watts, 43 watts. Temperature about 60 degrees, 56, 60 degrees. This is a fluorescent bulb. It's rated at 33 watts. Right now it's outputting about 16 watts, or it's using energy at a rate of 16. Temperature roughly 30 to 40 degrees. So kind of cool. And this is an LED rated at 8.5 watts. And it's only using 5 watts. It's very cool. And when I say cool, I mean temperature-wise. So really, incandescent bulbs, they're essentially heaters that also give off light, whereas an LED, most of the energy is just being used for light. So that's why you're seeing those temperature differences. An incandescent is essentially a candle. It's close to a candle. A candle, again, being about 80 watts. Bonus content. It's an LED is so temperature-wise cool that you can grab it, no problem. I would not do that with an incandescent. You can get hurt. Those temperatures get crazy hot. You should even let it cool down after turning it off. This is just like, it's kind of funny. I put the 75-watt bulb there. You see that there's nothing there, but it heated up my little stand. So you're seeing the heat signature. This is an infrared camera, so it's able to take the temperature. The one thing I want to say in terms of light bulbs, so LEDs super energy efficient, and the cost did come down in the past whatever decades since it's come out. So yeah, they're cost equivalent. It's almost more. It makes economic sense to immediately switch. It doesn't even make sense to like use up the incandescent. It makes sense to immediately switch if you get like a reasonably priced LED. I also want to say fluorescents, though they're more energy efficient, they contain mercury. So in terms of what goes into them, they're maybe not the most environmentally friendly. If you break one, you have to clean it up very carefully, otherwise you might breathe in the mercury dust. So if you break it, if you break a mercury or a fluorescent bulb, just be careful about cleaning it up. That's my spiel for today. Hope you enjoyed the video.